Hello, I'm David. I'm presenting our work, AVGuardian, detecting and mitigating publish-subscribe overprivilege for autonomous vehicle systems. This work was jointly conducted by our research team at University of Michigan and Professor Alfred Chen at UC Irvine. Robot Operating System is a common middleware for autonomous systems. It provides efficient real-time communication for overlaying software components to collaborate for mission-critical tasks. We find ROS is broadly used in emerging autonomous vehicle systems, for example, in popular open source platforms AutoWare and Baidu Apollo. AV software components are organized in a distributed manner. I will briefly lay out the key ROS nodes and their pulsar relations of a typical ROS-based AV system in this slide. First, the peripheral device driver nodes take ROS sensor input and generate ROS level sensor messages. Second, the key AV modules, including perception, localization, planning, and control, performs processing locally by subscribing and using messages published from others along this pipeline to generate a control decision for actuation on the physical campus. Because of the integration from third-party vendors, the peripheral device driver nodes are easier to be compromised and controlled by attackers. We make this assumption in our threat model. In our work, we investigate a new overprivileged vulnerability caused by the overgranted permissions in this PubSub communication channel in the context of ROS-based AV systems. We consider a threat model that an attacker compromises and controls a peripheral driver nodes and abuse the overgranted publish or subscribe permissions to publish fake message states or sniff privacy-sensitive information from this communication channel. We formulate two types of overprivilege with publishing or subscribing of messages at the message field level. Subscriber-side overprivilege happens when a field in a subscribe message is not used in the local processing of a subscriber, because the subscriber is overgranted with the subscribe permission for this unused field. This overprivilege may result in information leakage if some unused field contains sensitive information and the subscriber node is controlled by the attacker. Publish-side overprivilege happens when the value of some field in a published message is directly copied from messages that the publisher subscribes to. In other words, the publisher only copies these fields without changing them, but the granted publish permission allows both value copying and modification, which thus grants more than what is needed. This overprivilege may result in information spoofing in the publisher node if it is controlled by an attacker. In safety-critical systems, like AVs, this may cause severe safety consequences in the real world. We discovered that both publisher and subscriber-side overprivilege generally exists in popular AV software platforms, including Baidu Apollo and AutoWare. The goal of this work is to mitigate this overprivilege by enforcing a fine-grained permission control model in the PubSub communication channel for AV software systems. In particular, we developed novel static analysis methods to systematically detect all subscriber and publisher-side overprivileged instances in input AV software code. Then, a set of permission control policies is automatically generated based on the static detection results, and they are enforced at the AV runtime to mitigate the overprivileged vulnerability. In the static detection phase, we track the usage of each subscribe message field at a subscriber node through depth use analysis of the subscriber's code and label the unused fields as subscribe-side overprivileged instances. To detect publish-side overprivilege, we apply 10 analysis to the AV modules to discover any direct copy from a subscribe message field to a published message field. To prevent blocking legitimate functionalities caused by removing true PubSub permissions by mistake, zero false positive in the overprivilege detection needs to be achieved. To defend against potential exploits of detected overprivilege, we developed a runtime mitigation component to restrict the access or manipulation of the overprivileged fields. This runtime mitigation component must be able to defend against the threat that an AV module is compromised. Code-level policy instrumentation on an AV module does not work under this threat model. We made this runtime component operate within the ROS middleware, and it is thus transparent to AV modules and is able to defend against this threat model. The extensive use of virtual functions and asynchronous event callbacks in a complex C++ code for AV systems can lead to false positive in the overprivilege detection. We make conservative assumptions on the binding of virtual functions and ordering of event callback invocations within an AV module to capture all possible control flows at runtime in performing our static analysis. These customizations effectively reduce all 30 false positives in the overprivilege detection of a popular AV software platform, Baidu Apollo. Our prototype static analysis tool uncovered in total 581 publish side or subscribe side overprivileged instances in Baidu Apollo version 5.0. Among them, we identified the following cases with severe real-world safety implications, like vehicle collision, or privacy implications, like sniffing of vehicle identification number. We will show two concrete attacks that we successfully constructed in the following slides. In both attacks, an attacker compromises a peripheral device driver node for GNSS, a LiDAR device, both of which publishes a preprocessed sensor message topic containing a published overprivileged field. The attacker abuses the overgranted publish permission of this overprivileged field by adding its value with some offset or setting its values with constant at publishing. The protection node subscribes and uses the modified fields to generate perceived obstacle output. The first attack, obstacle relocation attack, causes relocating the position of obstacles that AV perceives from one lane to another. The obstacle removal attack causes AV fail to detect any obstacles in its surroundings. In simulation of both attacks, an AV collides to a front obstacle that its perception fails to detect. This is the attack that relocates the perceived position of obstacles from AV's current driving lane to other lanes. In the upper video, without the attack, the AV is able to detect obstacles on a same lane and stop in front of it. In the bottom video, when attack happens, AV makes the decision to keep moving since it thinks that the obstacles in the front are on the other lanes, and a collision happens. This is the attack that removes all obstacles from AV's perception view using the same traffic sync. In the bottom video, when attack happens, AV makes the wrong decision to keep moving since it thinks that there are no obstacles and a collision happens. To summarize our work, we performed the first in-depth study of overprivileged attack surface in the publish and subscribe communication channel of ROS-based AV software systems. In particular, we developed a novel static analysis method and also an AV module transparent defense solution to mitigate this new type of AV domain-specific overprivileged vulnerability. We also perform responsible disclosure of our constructed attacks to the Baidu Apollo developer team and receive confirmation that our exploits are valid and they are in the process of addressing them. That's all for my talk. Thank you for your attention.